Okay, today we're going to be doing the Lagrangian of inclined plane. We have an inclined plane with two masses and a pulley, gravity downward, and we have our Lagrangian right here and our other Lagrangian because we're going to do one with friction. So the first thing we need to do is find out kinetic energy, and we know that the Lagrangian is equal to the kinetic energy minus the potential energy, and that the kinetic energy can be written as 1/2 mv squared or 1/2 mx dot squared. So we're going to find out kinetic energy for mass 1 and mass 2. So this will be, the kinetic will be equal to 1/2 mx dot squared for mass 1 plus 1/2 m2 x dot square. And we could write this as the kinetic, putting everything simplifying, will be 1/2 m1 plus m2 times x dot square. And our potential energy, right, this will be minus the potential energy for mass 1 minus the potential energy for mass 2. Our potential energy for 1 is going to be, we could draw a triangle from here, right, from here to here. We'll call this angle right here theta, because this theta here is the same as theta here. And we could call this height here y. So our potential right here will be the opposite of an x. So it will be m1g x sine theta, right? And our potential for mass 2, well, if this whole rope is length L, and this side right here is x, then this side here will be L minus x. So the potential for our mass 2 will be m2g times L minus x. So we could write our Lagrangian as, remember this is negative, as our Lagrangian as 1/2 m1 plus m2 x dot square minus that'll be plus m1g x sine theta plus m2g L minus x. Then we can use our equation. We can find the derivative with respect to time of the partial of L with the partial of x dot. The only thing that we have with x dot is this right here. So the 2 will cancel with the 2, and we will have that m1 plus m2 is equal to x dot. And if we want to take the derivative, it will be x double dot. Now we can find the partial of the Lagrangian with respect to the partial of x. And this will be, we only have an x here, and we have also an x here. So right here, this x right here is going to be gone, and I will stay with m1g sine theta plus this x will go, but then due to the chain root, we will stay with times and minus 1. So it'll be plus minus m2g. So now we could write our equation of motion as x1 plus m1 plus m2 times x double dot plus m1g sine theta minus m2g, and all of this must be equal to 0. So if we want to find our x double dot, our acceleration, it will be minus m1g sine theta plus m2g all over mass 1 plus mass 2. Now, if we want to find it with friction, we have our Lagrangian already, right? We take the derivative with respect to time of the partial of L with the partial of x dot and the partial of L with the partial of x. And we'll get that this is going to be, if we take the partial right here of the Lagrangian, it will be equal to m1 plus m2. The 2's are going to cancel. I'm going to have an x dot. If I take the derivative with respect to time, I get double dot. And then for the same thing, we have here, right here, and right here, x, which will be m1g sine theta minus m2g. So then we could write our equation of motion as m1 plus m2 x double dot plus m1g sine theta minus m2g, and this is going to be equal to minus the force of friction. Where's the force of friction? Remember, the normal force is here, and the normal force is m1g cosine theta, and friction is mu, right? So we will have to write this down as m1 plus m2 x2 dot plus m1g sine theta minus m2g, and our force friction will be minus mu m1g cosine theta. And now we could find for our acceleration, x double dot will be equal to minus mu m1g cosine theta minus m1g sine of theta plus m2g, everything over mass 1 plus mass 2. And we can simplify this even more by saying that x double dot is equal to minus m1g times mu cosine theta plus sine theta plus m2g all over mass 1 plus mass 2. And this is our equation of motion or acceleration with friction. This one here is without friction, and this one here is with friction. So if you like this